Hi, so today's video is going to be the continuity of Chapter 1. As I said earlier in the last video, this remaining part is actually called photospectrometry, and it deals with measuring the so-called absorbance or transmittance of light through a substance or a sample of a certain substance that we would like to characterize or to know about its concentration, for example. So let us start this video with an embedded clip that I have taken from this source. So the Professor Dave Explains YouTube channel. It's a nice introduction that covers nicely the idea, and then we will go forward with the slides and go through some applications to test our knowledge. So I will start with the video.
As we have learned in a previous tutorial, kinetics is the study of reaction rates. Sometimes we will want to know how quickly or slowly a chemical reaction will happen. Therefore, any kinetic study will require monitoring the concentrations of a particular reactant or product over time to see how quickly they are being used up or formed. Of course, we can't see molecules and count them. They are just too small and too many. So to do this, we have to be clever. We can measure the mass of a precipitate as it is forming, or we can measure the volume or even the pressure of a gas that is produced over time. But what if a reaction does not produce a product in a different phase than the solution? Luckily, one of the most reliable methods involves using spectroscopy, which is the study of how light interacts with matter. So let's learn about this technique now. All molecules absorb and emit light differently based on what kinds of covalent bonds are in the molecule. If the products and reactants interact with light differently enough that there is a color change as the reaction occurs, we can monitor this process with an instrument called a spectrophotometer in order to measure changing concentrations. This will give us data in the form of an absorption spectrum, which displays how much light through a band of frequencies is able to pass through a sample to reach the detector. Where there are peaks, it means that not as much of the light of that wavelength is getting to the detector, which means that it is being absorbed by the sample. If we collect data like this continuously over the duration of a chemical reaction, we can gather information about how rapidly the absorbance changes, and thus how the concentration of a particular substance is changing over time. In order to do this, we will use an equation that relates the amount of material in a sample to the absorption of light passing through it, and this is called Beer's Law. Here, A is for absorbance. This symbol represents something called the molar absorptivity, a measure of how well a chemical species absorbs a given wavelength of light. B represents the path length, or the distance light has to travel through the sample, which is relevant because the more of a substance the light travels through, the more of it that will be absorbed. And C is the concentration of the sample, which again is relevant because the more concentrated, the more absorbance that will occur. Absorbance is measured by comparing the intensity of the beam of light as it enters the sample and the intensity as it leaves the sample and strikes the detector, which are I0 and I respectively. And A will be equal to the log of I0 over I, or equivalently the negative log of I over I0. If we plug the latter version into the original equation substituting for A, and then solve for I, we can get this version of the law, which displays the exponential relationship between variables that are easily measurable. The primary advantage of this technique is that we can just let a reaction occur normally and measure the rate indirectly by analyzing the light that interacts with the components in solution, rather than stopping the reaction and measuring concentrations directly. Let's try one calculation to put this into context. Say that a substance has a molar absorptivity of 0.35 inverse centimeters inverse molarity. Light passes through a 2 centimeter sample and hits the detector with an intensity of 0.12 compared with the incident beam. What is the concentration of the sample? If we want to use the more basic version of Beer's law, then first we need to calculate the absorption. We can use this simple equation from before, plugging in 1 for the initial intensity and 0.12 for the other intensity. That gives us 0.9208 for A. Then we will use Beer's law. We can rearrange to solve for C, our unknown, plug in the absorption we calculated, plus the two given values, and we should get around 1.3 molar for the concentration of the analyte. Gathering this kind of information regarding concentration and plotting it in real time using computer software will allow us to easily infer all kinds of things about the rate law and hence the reaction mechanism for the reaction that is happening in solution, which is incredibly useful data.
Okay, so as you have seen, excuse me, this video explains basically how things happen if we want to understand or investigate concentrations or properties of absorbance or absorptivity and transmission or transmittance of a certain substance. So basically this is called spectroscopy, as he said, because there is a light beam that goes through the material and interacts with it. So here it's a bit repeating things, but I'm going to add the concept of transmission or transmittance. Basically we have an incident flux of light that has an intensity or a flux of phi 0. He called it I 0. It goes through a sample, through a substance, and then only phi t of it is transmitted. Then as you have seen, the absorbance of the substance is basically the log base 10 of phi 0 over phi t, so the incident intensity over the transmitted one. However, we define the transmission as being the ratio of phi t over phi 0, and it's in percentage. So we calculate it as a percentage of the transmitted light intensity. Now if you look at these two, let me just do this. Well, if you look at these two, this one and this one, we can actually find a nice relation, which is easy to understand. Well, it's not written here, so I will write it, which is basically at the end, A can be written as the log 1 over t. You noticed? Because 1 over t is phi 0 over phi t. So 1 over t. Now why is that relevant? Because in some cases you actually have the transmittance or the transmission of a certain substance. So if you know that, you can actually get to A through this relation. Great. Now there is some laws with which we can actually deal with the absorbance or the absorption of different substances. And this example here will show you, for example, the addition of absorption. It might sound intuitive, but it's not necessarily always the case. So here we demonstrate that. Imagine that we are in a situation where we actually have two substances, a substance called, let's say, J, and another substance called B. And then we send a beam of light with an incident beam intensity phi 0 that goes first through the first substance, then a part of it is transmitted, let's call it phi 1, and then after this one we put another substance, B, and then the outcome of the entire setup is phi 2. So we have phi 0 incident, phi1 going through first substance, and then phi2 going through the second substance after phi1. And we can actually also mix these two together in one container, and then send phi0, and then get at the output phi2, which is the same. So basically this means that having these two in series, the one after the other, is similar to mixing them. But let's do the calculations. Now, the transmission T1 through the first substance is simply phi1 over phi0, and we just have seen that before. And then transmission through the second substance is phi2 over phi1. Now, in the other situation where we have mixed both, then transmission of the mixed solution is phi2 over phi0, which we can write phi2 over phi1 times phi1 over phi0. So you can easily see that it's T1 times T2, and T1. So the transmission is the product of the transmissions of two substances put in series. That's the transmission of the solution, of the mix of them. So, as I said before, A can be written as log 1 over T, which is equivalent to minus log T. It's the log rules, if you inverse the ratio. So it's minus log T1 times T2 for the mixed solution. So if you do the logs rule of multiplication, then this can be written minus log T1 plus minus log T2, which each one of them is, this is the absorption of, or absorbance of solution 1, and this is the absorbance of solution 2. So basically at the end of the day, if we mix two solutions or two samples, two substances, then the absorbance of their mixture is basically the sum of the absorbances for each one of them. Okay? Now, as you have seen in the video, the Beer-Lambert Law, or he called it simply Beer's Law, or Beer's Law, it actually allows us, from the absorbance that we can actually measure experimentally, to come up with the concentration of the molecular compound in a certain substance. Now the relation, as mentioned before, it's A, which is the absorbance, equals to epsilon times L, with L being the distance or the path through which the light is moving for the substance. Basically L is the dimension of the recipient or the container, and C is the concentration of the specific compound that we are looking at. Epsilon is the molecular absorption coefficient, or in another way it's also said the molar absorptivity. It defines how much the specific compound or the specific molecular compound that we are looking at in a solution, how much it absorbs light. Okay? So the units, absorbance is measured in unit of absorption. So it's like an arbitrary unit. The molar absorption coefficient or molar absorptivity is in centimeter minus 1, mole minus 1. I think the L here is wrong. And the solution concentration is in mole per liter. Here actually the liter, it's liter, I'm sorry. And the light path is in centimeter. Now what's important to notice is that the Beer-Lambert Law, or the Beer's Law, applies in the case of solutions with very low concentrations. Now obviously I do not have the numbers now on the top of my head, but when you have very high concentrations, interactions become different. So the Beer-Lambert Law is sort of an approximation, but it works very fine for most of the concentrations of most of the solutions that you use or people use in their research. Okay? Now what happens if there is a solution that is made of several elements? Now we have seen just in these two slides before that if there is a solution made of several elements, then the absorption of the solution is equal to the absorptions sum of absorptions of each of the elements. But that is for the absorption. Now, how the Beer-Lambert law applies if we have a solution that has a mixture of different elements. Now, when we have a mixture of different elements, each molecular elements would have a absorptivity, a known value of absorptivity. So you notice that epsilon I corresponds to the absorptivity of the element I in the solution at a given wave number, or wavelength, because absorptivity is wavelength dependent. Okay, meaning that, let's say, take a molecule called F. Then this molecule, if you send a red light, it will absorb it differently than if you send a green light, with a different rate of absorption, with a different absorptivity. Okay? So, if I go back one slide earlier, it's epsilon LC. That is for molecular solution that has one molecular element in it. Now, the same thing applies when we have several ones. L will not change because the mixture will be put in the same container. So for all the molecular elements, the light will go through the same container, so the distance does not change. But epsilon I times Ci, which is the concentration, Ci is the concentration of the element I inside the mixture, we actually multiplies L by the sum of epsilon I times Ci. And this is the general form of the Beer-Lambert law. As an application for this, it's very simple. I mean, after I finish this video, I will post it, and then I will do another video or another session where we actually solve problems. And I will post the exercise sheet and the solution sheets into the web page, to my web page, where you can go and check it. This is a sort of example of how actually things could be proposed for this application. So the situation is the following: a radiation having a wavelength of 280 nanometers, so we are sending light at 280 nanometers, that goes through a 1 millimeter thick aqueous solution of tryptophan amino acids. So the length of the container, or the length of the solution, or the path of this radiation of light is 1 millimeter. The concentration of this amino acid is 0.49 millimole per decimeter square, a cube. So now if you look at this, let me write things a bit in this. So here we have L, and here we have C, and here we have lambda, right? Then, one additional information, he says, the intensity of radiation beam is reduced to 52% of its initial value. So which means that the final value, phi transmitted, is 0.52 of the initial phi 0. This is what that means, right? So this expression reads exactly as the text. The intensity of the radiation beam is reduced, which means when it's transmitted, it is reduced to 52% of its initial value. So it's 0.52 of the initial value phi 0. Okay? Then from this we can get into T, which is the transmission. T is phi T, right, over phi 0. This is what we've seen before, which is actually going to be 52%, or 0.52. So we have the transmission, which means we can get into what? The absorption, or the absorbance. Now, the first question is calculate the absorbance and the molar absorption coefficient. So he wants here, let's put it like this, here he wants A, And also he wants the molar absorption coefficient, or the molar absorptivity is epsilon. That's what we need. A is equal to how much, and epsilon is equal to how much. Well, if you look into the solution, A is equal minus log t. And we've just seen that t is 0.52. I explained it in the earlier slide. So we calculate A, which is minus log t. That's simply the solution. Now to get to epsilon, we use the Beer's law, which is A equal epsilon C times L. We have C, we have L, we solve for epsilon, and we have these values. Now notice that we haven't changed here necessarily we just changed 0.1 centimeters to get actually into the centimeter unit, because it's the international unit. But we kept this in mole decimeter cube. So we've got epsilon, the absorptivity or the absorption coefficient, molar absorption coefficient of this solution. Now the question is, determine the transmittance. So here he wants us to determine T in the second question. Now T equals how much? If the cell or the container is now 3 millimeter thick. So now we have a new L. Let's call it L star. But we know epsilon. So we have epsilon. We have a new L. We have the concentration also. We just need to get to T, which is easy now. I mean, just A is equal to epsilon. So this is epsilon that we've just found, times this is the concentration that we just calculated, times the new L that I called L star, that it's given 3 millimeter thick. So just plugging this together, making sure of the units, we get into the absorption. The absorption is 1 over, so transmission equals 1 over A. Or actually, no, I'm wrong. Sorry. Actually, A equals minus log T. So if we want to solve that, it's just exponential, right? So exponential minus A, or sorry, again, the exponential here is, the log here, sorry, is base 10. So if you want, like, write it like this, log T equals minus A. So if I do the exponent of it, so I will get 10 to the power minus A equals T. And that's it. Okay? So this is the simple application of things. Now what I will do is, I'll write it here as a sort of training homework, if you want, for those who are interested. Training work. Please work out the exercises. The exercises in sheet of chapter 1. Okay, that I will post into the website. Thank you for watching that, and if you have questions, we will walk through them later. Bye-bye.